Good morning. It is my pleasure to provide this lecture as part of Lectern Session 1443 in this TRB 2021 annual meeting. The session is about data acquisition and geologic modeling for decisions from network scale to site scale. My name is Jean Hutchinson, and I'm a professor of geological engineering at Queen's University in Canada. The title of my talk is Rock Slope Hazard Modeling Informed by Remote Sensing, Next Steps. As you've seen from the title of the session, we're focused on the type of data we can acquire to support decisions in rock slope management. In this case, we're looking at remotely sensed data, and as you'll see, this is transforming our understanding of the processes and behavior of these slopes. The data can be taken from aerial, oblique, and/or terrestrial vantage points, which means you have either a straight downward look, a look from the side, or a more horizontal look in each of these cases. LiDAR and photography are being used extensively, and increasingly INSAR is also being used to collect this information. In the image provided here, you can see the different platforms and some idea of the ranges at which they acquire data. The data sets can be single or they can be time sequential. And in time sequential, they can be on a matter of days, weeks, months, years in terms of the repeat time for data acquisition, or they can be more continuous. And as you will have seen a moment ago from Gabe Walton in this same session, he has demonstrated the value of the more continuous data collection and what you can learn in terms of rock slope management from that kind of data. Some emerging tools are also being applied in some circumstances, including hyperspectral analysis and thermal analysis. Some of you may have seen the talk by Matt Lotto on January 6th in the subcommittee meeting for geotechnical asset management. But in that presentation, Matt talked about the scale of data collection and the scale of data analysis. And he very nicely demonstrated how you can move to regional scale movement screening and integration of multiple data sets to make decisions about infrastructure. So on this image, you can see from the left side a highly detailed change detection result from more localized site-specific analysis across to corridor scale in the center through to regional scale on the right. And what Mac talked about was using this as a screening tool, and increasingly we're able to also use these larger regional scale data sets for detailed analysis as we work out the processes at that more local site scale. This slide presents some ideas around a decision framework whereby we can look at rockfall assessment and integrate the remotely sensed data I've been talking about, but also considering pre-failure detection of these potential rockfalls. So as you can see, there's network scale, corridor scale, and site scale processes that we have defined. In the first phase, the search phase, we're looking for identification of higher rockfall risk corridors at the network scale, moving through to, at the corridor scale, finding sites with moving or missing blocks, and then at the site scale, looking at blocks that have either been detected prior to the rockfall event and are continuing to move, or looking at sites where potential blocks have been detected but are not moving, or in back analysis after an event. We then move to the phase 2, the action phase, and to phase 3, the learning phase. So in the action phase, we look at the consequence of these events. We make some forecast of the failure potential, and then we think about a response to those potential events. And one of the key distinctions here is when we have some sense of the rockfall in advance of the event, we can estimate the size, the runout, the impact intensity, and we can monitor that moving block and make an estimate of when the rockfall is likely. On the other side, when we don't really have any advanced notice, what we do is work with previous events and try and identify similar potentially unstable blocks from previous knowledge, and then consider the triggering events that may control rockfall timing. So this is a much more conceptual approach, but important nevertheless, because there are many cases where we don't have detection of these blocks before the events occur. One way that we can look at the network scale, as I mentioned, is to work with satellite INSAR. This is an image over a fairly large area associated with railway track rock slope instability. And you can see in this image that the change detection from the INSAR satellite data provides us with some focus points to move into a more corridor level of analysis. This is an example of searching for rockfall source zones at the corridor scale. This work was completed by Richard Carter in his master's, and he worked with aerial LiDAR and the information you can gain from both the point cloud as well as the color that is derived from photography. Combining these two data sets permitted him to think about sections of the slope which were exposed rock and which were either source zones or talus deposits. The results of Richard's work can be seen here, where he's identified rockfall source zones that are rock, or sections of the slope which are steep enough to be rock but don't show up as rock from the photo analysis. Likewise, determining locations where there are flat benches, fans, or talus deposits on the slope. And you can see in the legend in the bottom right that we see an identification of plains and benches, fans, talus slopes, and rockfall source zones. And this image shows the results of that work, where we have semi-automated terrain classification identifying source zones, but also in the inset image identifying forest, which can be a helpful deterrent against the movement of rocks down the slope. Richard also extended his work to think about the consequence of potential failures from the identified rockfall source zones. So in this case, he's moving into phase 2, the action phase of this rockfall analysis process. In this diagram, you can see the results of the work thinking about moving down the risk chain on the bottom left from conditioning of the slope through triggering, leading to a rockfall, and then in this case, thinking about the run out of that rockfall and the potential for it to impact the railway track at the base of this slope. Again, considering the presence of trees and their potential to help mitigate the effects of those rockfalls. Now we'll focus in at the site scale. So this is the case where we have, in this case, terrestrial LiDAR data taken from several hundred meters away across the valley from this slope. The slope geometry is represented by the points on this image that have X, Y, Z positions and intensity, and in this case the data is at about a 7 centimeter spacing. What you can see is a representation of the geometry of the observed physical object from this work. When working with data from a single acquisition at site scale, we can start to extract information that helps us in our decision making. This is work ongoing by Yannis Farmakis, who is a PhD candidate in my group. Here we see on the left the data acquisition that we've already been talking about, and what he's working on is our ability to extract knowledge from these images to define specific entities on slopes. And in doing so, we support the decisions around rock slope management by automating some of these processes and by also making the data interoperable with other data sources that help inform our results. But in this case, a single data acquisition gives rise to our ability to detect different features on the slope. We see the results of that work in this slide. On the left side, we see an inset of the slope that has been evaluated by Yannis and David. You can see in this image the zone of talus movement down the slope over the rock shed. You can see the outcrop sections of rock on either side of that talus channel, and you can see locations where talus is resting on benches in the slope. The objective of Yannis's work is to really identify what is rock outcrop, what is a debris channel, and what is constructed infrastructure. And you can see some of the information that's required in the level 2 circle in the middle of this diagram, whereby you're trying to identify what's an outcrop, what's a bench, what's a rock shed, etc. If we then move to the right side of this diagram, we can see the automated process moving from bottom left here, from the original LiDAR data set, to a first stage where you identify the distinction between a debris channel and other, and then moving on through this sequence of analyses as the data is automatically processed, we can eventually get to a position where we have individual objects that have been identified that represent different parts of the slope. And so that shows us the outcrop areas, the talus areas, and the constructed infrastructure. In this slide, we get a sense of what we can do when we have remotely sensed data at different times, and we can do change detection. This is at the site scale. So that change detection permits us to identify locations where we have ranges of volumes of material moving away or falling from the slope, and we can see those volumes here on the top right. What's shown in the image are the larger volume rockfalls that have occurred over a 3-year period with the volume attached. And so this gives you an idea of the kind of information we can get when we have time sequential scans. Now these are taken every few months, in contrast to, again, Gabe's work, where he's getting much more continuous data, as we saw in the previous presentation. Now we move back to the decision framework and start to think about the movement detection before the rockfall event occurs. So we're here in the middle part of this diagram. This is an example of a situation where deformation and precursor analysis permitted us to understand the potential failure upcoming. What you can see around the eventual failure is a whole series of smaller failures that outline the boundaries of this rockfall. And so this gives us some idea that a possible failure might be occurring in the future and permits us to think about modeling the phase 2 action items. This is another example where we also see deformation prior to failure, which gives us an idea that a failure might be about to occur and permits us to do an analysis of the patterns of deformation and the rates of deformation prior to that failure. With more information of this type of event, we can start to move towards defining warning thresholds of magnitude of deformation and rate of deformation prior to failure. When we track deformation, we're often able to identify the direction of the movement of a block. So in this case, you can see over a 2-year period in the stereo on the right, the movement of that block, and you can see that it fairly continuously follows the direction of joint set 3 identified in this failure. Post-failure, we can look at the shape of the block and do some further analysis on the kinematics of that and on the definition of thresholds for warning. As noted before, once we identify the potential for a failure, we would like to estimate the size, the potential runout, and the impact intensity of the rockfall event. In this image, we see an identified block because of the precursors prior to failure, and then the state of the rock slope post-failure. When we look at this information from the change detection perspective, we can see the zones where rock has been removed from the slope by the failure, where further rock has been removed from the slope by the impact of the fragments of that rockfall moving down the slope, and we can see the zones of deposition on the talus cone and on the slope of the fragments of that rockfall event. And when we do a stereo net analysis, we can see the classic evaluation of a planar and wedge sliding failure. In this short video, you see the result of running rockfall simulation models using physics engines on the case that we identified on the previous slide of a potential failure. So you see the rock fragmenting as it vacates the backscarp of that failure surface. You see it impacting the slope as it moves down. You see it depositing partway down the slope and on the rock shed. And you see that most of the volume of material moves into the canyon beyond over that rock shed. So we can use these calibrated models to forecast failure event outcomes in a probabilistic sense. On this slide, we can see the results of the simulated change on the right compared to the actual change on the left. And what we can see is a reasonable agreement between the percentages of volumes that are resident on different parts of the slope. This gives us some confidence that the fragmental rockfall simulation using the physics engines is an avenue of research worth pursuing. In this image, we see the results of using the simulation we saw on the previous slide to think about the impact of rockfalls on ditches and, in this case, the railway track locations. Here we see the results of several analyses permitting material to build up as the slope continues to fail. And what we show is the volume of rock that falls within a 95% of runout and outside that 95% of runout. And what you can see is that outside of that 95%, the 5% has a chance to have an impact on the track in this location. Further work is being done on calibrating these types of models to think about fragmental rockfalls and further developing the physics engine implementations through an emerging pooled fund project 5459. And the lead agency for this is WSDOT, and Mark Fish is the contact. And if you're interested, his email address is shown on the right side of this slide. The final component of this session, besides the scale and remotely sensed information, is thinking about geologic models and how they should be incorporated into this work. In our work, we've been thinking about different geological settings and trying to understand the failure modes that we can ascertain from doing back analysis of this type of remotely sensed data. Key steps for future work in this area are to continue to use remote sensing data with its higher temporal and spatial resolution to better understand process models that help us define what the failure modes are and what leads to those failures. We need to continue to evaluate slope deformation and processes related to these geological settings and assess a variety of settings. And then we need to use observations to support slope management decisions, including potential for pre-failure detection and defining deformation rates and magnitude thresholds to provide warning. On the right side, you can see similar work to what I've already shown you, in this case on a Quaternary glacial deposit, where we have a different mechanism and a different sequence of events that lead to failure, and in back analysis we can start to evaluate those impacts. Overall conclusions for this talk and related to the development of these data analysis and remote sensing tools are that they enhance our understanding of events and the associated details a great deal, permitting us to build databases, and that lets us calibrate the types of models you've seen and also helps us try to identify warning thresholds related to failure modes. We work with past events, moving towards forecasting when we are able to calibrate these models, and in particular this permits us to anticipate the effectiveness of mitigation. This work is mostly being done in an open source environment in the research program, and this is to many people's advantage because they can then carry on from and benefit from the research. I didn't talk about it, but you can do this type of work at different levels of data quality with equipment that ranges from the cost of your phone, especially increasingly, to much higher costs. And as I hope you've seen, this can be applied at different scales. The details and methods are often being developed at the local scale where you have more control on the variability of the information, but then you can expand that to broader scales, so moving from site to corridor to network scales. In conclusion, I'd like to identify the enormous contributions from the project team, both from the perspective of the two main Canadian railways, CN and CP, our co-collaborators, University of Alberta, as well as the Geological Survey of Canada and Transport Canada, and a very large number of students and professionals have worked on this project over the years, and you can see those people on the right. You can also see highlighted with red stars some of the people who have done their degrees or done their work in this program and who've made presentations here at the TRB this year. And in conclusion, I'd like to thank you very much for your attention. Should you have any questions about this presentation, I'd be delighted to hear from you at the email address shown at the bottom here. Thank you very much.